I want to give you guys a quick run through on turning a 234 tree into a red-black tree. I figured it's worthwhile to just go over a few things about red-black trees anyway. My hope in putting together this document in this short little step through video is that it's going to give you something like more useful for studying than the in-person, well, the in-meeting session that we missed tonight. So, okay. Red, black trees. The whole point is to keep that logarithmic big O of a binary search tree, pretty much just to keep it balanced. So, some quick insertions. We have a perfectly balanced tree right here. 2 red paths on each. Add one in. In the way, because you can't have 2 red... Actually, let me go over the rules first. Okay. Red-black tree rules. Every path is either red or black. Yes. Root is black. Yes. One rule that I didn't write on here, but is a rule, is that all the leaves have to be black. But since for all these demonstrations, it seemed like it would be a tedious task to draw little legs on the bottom of each of these nodes to represent leaves, I figured we're gonna just bear that in mind for now. If the path to the node is red, both of the children are black. So we can't have a red and a red, but we can have a red, a black, and a red. And yeah, again, the same number of black paths in order to get to any leaf on the tree. So, the insertion algorithm, you put it in like a regular binary search tree, like how I inserted 4 right here, and it lands right where it would land with a regular binary search tree. But it went through this path of 2 reds. So we did a little color flip. We cleared out this red, turned them into black, and then put a red in the path between 2 and 5, which is one of the steps if you pass through a node with red paths to both of its children. When you're putting in your new node, you color the paths to both of the children black and color its the path to that node's parent as red. And when you add a new node, you always add the new node with a red path. And then there are rotations, which I'm sure you know, but we're going to talk a little about them. Okay. I did some other rotations, but I stole this from the slides because I remembered looking at it and it just helped me understand. So we put in a node N3 that is greater than N1, less than N2. This is where it winds up. But alas, we have a red, and that's against the rules. So to flip it, to fix it, we flip it. So we flip it first and get it here so that this guy comes up and this guy goes down. Here we are. And then we have the center rise up to get this even tree, subtree. Okay. So, left-leaning red-black trees. It is a red-black tree, but they found an easier way to code it where instead of having to worry about reds on both sides, there's only ever reds on the left. Does the same job, less code. So, and again, this has rotations. So, the left rotation, obviously. And something I wanted to point out with rotations that I remember for me, it was like, wait, well, it was a little bit confusing. Is what do you do with the children nodes of what's getting rotated? And you put them pretty much where they can go. So if there's a node that's connected to A that's less than A, like that's going to be untouched. That's going to be fine. That much is clear. But for a node that is, the way 6 is to 7, where it's between 5 and 7. So for here would be a node C that is between A and B. When you rotate it, it hops from B to A. Thought that was worth mentioning. Right rotations, it's a left-leaning tree, so nothing's gonna stay right, but we're gonna have to rotate right sometimes to get to where we want to go. And then color flips. So if we look at what the point of it all is, which is to have the same number of black paths from the root to the end leaf for every end leaf, then this makes a lot of sense. This is like, oh, of course I can just do this, because if we're looking at these 3 items, having a red up here and 2 blacks down here, pathwise going from the root to the node, or from the root to an end leaf, is really just the same thing. Okay, so we want to transform a 2-3-4 tree into a left-leaning red-black tree, and that is a very doable task because they're so similar already. So earlier we had that great 2-3-4 tree generator that we used to test out problem 1, and it gave us this. So we have an understanding of the 2-3-4 tree. 1 is less than 2, 3 and 4 between 2 and 5, 6 is between 5 and 7, and then 8, 9, and 14 are all above 7. So a 2-3-4 tree is really the same thing drawn differently as a red-black tree. And I hope that I can show you that in this example. So here's how I did it. I just drew the lines right on to help us start up this visual. And the boxes and all of it, it's all just for the visual. So I drew the lines to better relay that, that really is the relationship of these. Like we could convert this into a binary tree, and 5 would be the parent, 2 and 7 would be the children, and then over here 9 would be the parent, 8 and 14 would be the children. Like it's that's the actual setup, even though in a 2-3-4 tree you just draw it differently. These could go either way depending on what specific heuristic you're looking at. Like, do you want the lower one to be higher or the... So I did the lower one just because that was what we had kind of talked about earlier. So you see that these are really the same as this, which is a perfectly balanced red-black tree. And each leaf, each imaginary leaf, we shall say, because these are actually nodes with imaginary leaves that don't have little sticks on the end of it. Same number of black lines away from the root. So here's our 2-3-4 tree. However, that's not what we want. We want a left-leaning red-black tree. So maybe I should bring this down here. Make it a little smaller, whatever. We start off with this, and as you can see, it's breaking some left-leaning red-black tree rules right off the bat. So we can't have these two. You see how so I'm going to get rid of those. I'm going to start with the 9, 8, and 14, and I just flipped these colors. I flipped the red 8 and the red to the 14 into a red between 7 and 9. If we check, that's color flipping, that's okay. However, now we have two rules broken, and we have a red line on the right connecting 7 and 9, and right above a red line connecting 5 to 7. But fret not, because we can get rid of this path from 5 to 2 and this path to 5 to 7, because the root node 5 has two red paths to each of its children, and we know we can swap that out for two black paths. So now we have this. Our two red paths left over are both right-leaning, but these are simple enough rotations, and we can fix that. So I'm going to start with the simpler rotation, which is obviously 3 to 4. We just swap these spots so that it goes 2, 4, 3. Boom. 2, 4, 3. Our tree is intact. We're in good shape. And our final transformation, I guess we'll call it, is to take this right directed path from 7 to 9, and since it's a left leaning red black tree, we need to make it left directed. Should fix that spacing, I guess. I'll do that before I send it out. So the way we do that is by flipping the 9 over here, and what we have then is an 8 that doesn't know where to go, a 7 and a 6, and then a 9 to a 14. So we latch the 8 onto 7 because that's really the only place it can go. It's less than 9, greater than 7. So this is just the perfect home for it. All right, and we are done. I'm free tomorrow night. If you guys want to go over other problems, I'd be glad to. All right, thank you so much. Goodbye.